Hi. So in this lecture on section 4.4, we're going to talk about work. We're going to talk about what is work, what is an open system, and then what is a conservative force and a non-conservative force, and why would that be important to know when it comes to work. So we'll start with the definition of work. When dealing with a closed system, we see conservation of energy. However, if we are not dealing with a closed system, if we are dealing with an open system, then we can see a change in energy within that system. And that change in energy is called work. So that is actually the first definition for work. Work is abbreviated by a capital W, but we can say that work is equal to a change in energy. Now, in order to understand why sometimes systems have conservation of energy and why sometimes systems have work done on them is all based on whether or not they are an open, or largely based on whether or not they are an open or a closed system. So let's, since we in the previous lecture defined closed system, let's define now open system. So an open system is a portion of the universe chosen for analysis which exchanges mass or energy, all that kind of stuff with its surroundings. So we're really talking about systems that don't include everything that's relevant to the interaction. So for example, if you have a car crash, if we look at both cars involved in the crash, right? So we're looking at a closed system, then we would see that energy is conserved if we looked at both cars in the crash. But if we choose to only focus on one car in the crash, and we completely ignore the other car, then what we would see is that the energy of that particular car changes. And so that particular car, we would say, had work done on it. Okay. Now, this is not the only definition for work. This is really only the first definition for work, which, by the way, is shown to you on the equation sheet. So you'll see it on there. But there is also a second definition for work, and this is more of the textbook definition of work. In order for an object to work on a system, there has to be some kind of force involved, and the system has to undergo some sort of displacement. So that's what you read when you read about more of like the textbook definition for work, right? It's a force exerted on an object across a distance or across a displacement. Now, I should note that that force cannot just be in any direction. It has to be in either the same direction or the opposite direction of the displacement. And so that's going to be part of our definition, our second definition for work. So our second definition for work is that work is equal to a force multiplied by some kind of distance. And then to make sure that that force and distance are in the same dimension, so they're either going in the same direction or they're going in opposite directions, we're going to add a cosine of theta. Okay. And this is also given to you on the AP Physics 1 equation sheet. Now, let's talk about why that cosine of theta. Well, first of all, we should talk about two things. We should talk about why, in order for us to do work, the force has to be in the same direction or opposite direction of the displacement. So we're going to talk about that. We're also going to talk about how that idea is represented in this cosine of theta. We're going to do that by looking at three different situations. So let's imagine that we have some kind of force, we have some kind of distance. And let's imagine that we are lifting something up. So our force would be up in order to lift something up. and the distance that the object goes would be up. Now, the angle that we see here, right? Like what's the difference between the direction of those two arrows would be 0 degrees because those two arrows are going in the same direction. So there's no real difference there. And so cosine of 0 is a +1, meaning that if we take this force and this distance and multiply them together, we're going to end up doing positive work in this situation, which means that energy is added to the system. Which, if we think about it, that makes sense, right? Our example is we're lifting something up. And so when we lift something up, we're going to add gravitational potential energy to that object. So this mathematically, with this theta of being 0 degrees and cosine of theta being, or sorry, cosine of 0 being +1, thus telling us that we are doing positive work, we're adding energy to the system, all agrees with that idea that when you lift something up, you add gravitational potential energy to that object. Okay. Now, what if we have this object up high and we choose to lower it back down? Well, when we choose to lower it back down, the force that we exert on the object will still be up. It will just be significantly less than before, but it still is up, right? Even as we lower down, our hand would be pushing upward. But now our distance is in that downward direction. So what is the angle between those two arrows? Well, that angle is 180 degrees because they're facing in opposite directions. And so if we take 180 degrees and we stick it in, we say, what is the cosine of 180? We know that the cosine of 180 is -1. Thus, this is telling us that we are doing negative work. Okay, and so what does it mean to do negative work? It means that energy is being subtracted from the system. And again, if we think about the example here where we're saying, okay, I'm lowering this object down. Well, when you lower that object down, you are decreasing and lowering the gravitational potential energy in this object that you're lowering down. So that is consistent with what we're saying here, is that negative work is going to be occurring. Okay, and then we do have one last scenario. Let's imagine that we are still pushing up on this object, but rather than lifting it up or bringing it down, we're just moving it left and right. So you almost can imagine when a server puts the plates of food onto the tray and walks it out to the table that they are serving, right? So they're pushing up on the tray with all the food on it, but the actual displacement that they are undergoing is in that left or right direction. Now the angle between those two arrows would be 90 degrees. Okay, so this is an example where no work is going to be done. And again, if we think about it, that kind of makes sense, right? Like if we're just walking out, we're not moving this thing up, we are not moving this thing down at all, we're just walking it out to the customer, then we're not changing the gravitational potential energy of this object at all. So it makes sense that no work would be done. And the energy in the system stays the same. Okay, so the purpose of these outlining these three situations is to show you guys why we had to add in this statement that in the force and distance definition of work, that force and distance have to be in at least the same dimension. They either have to be in the same direction or they have to be in opposite directions in order to yield any work at all. If they are in perpendicular directions, no work is going to be done. Okay. Now, the other thing that I need to wrap up before we start doing some example problems is for us to talk about conservative and non-conservative forces. Because when you do work on an object, a force is doing it for you. And some forces are going to allow us to have a net work of 0. So sometimes we can do work on a system, but then, undo that work and end up with a net work of 0. And in other cases, that's not possible. And that is determined whether or not the force which is doing the work for us is a conservative force or a non-conservative force. So let's define those two terms. A conservative force is a force whose work done on a system is path independent. Okay, meaning that here, this is a little bit of a clarifying statement. If the system returns to the original position, then our work is going to be 0 joules. Okay, so the gravitational force is a fabulous example of this because we can move objects up and like do work on our system, right? So do positive work on the system. We can bring objects down, do negative work on the system. We can have the objects move all around, right? Up, down, all around. But if our object or our system returns to its original location, right? It returns to its initial position, then the amount of energy that it has remains the same as the beginning of the motion, and thus the work done would be 0. Now this is in contrast to a non-conservative force, which is a force for which work done is path dependent. Okay, a fabulous example of a non-conservative force is friction. We've used rubbing your hands together as an example many times with regards to this energy unit. And if you rub your hands together many times, you know that you are doing work because you feel that heat come to your hands, right? So you get some thermal energy from doing this work. Now, if I think about my hands, they largely start in the same spot and end in the same spot, right? I'm not moving them up, down, all around. However, when I finish and they are returned and end in the same spot that they started, I absolutely have done work because my hands are still warm. My hands still have that heat. Okay, so the path, the fact that my fingertips have moved, from the top of the opposite hand to the bottom of the opposite hand and up and down and up, even though we are repeating this path many times, because friction is a non-conservative force and is path dependent, all of that counts, right, as my distance. So that being path dependent is what makes this a non-conservative force. In the next video, I'm going to go through some word problems with you guys.